All right, welcome back to our recursion slides. I hope you have digested what we learned last time. It's a little hard, but it's really cool. And we stopped at a very interesting place. So we had that Fibonacci program. Let's copy it in. And surprisingly, it was not happy. I asked for the Fibonacci of 100, fib of 100, and though it could do the smaller one, it could not do the bigger one. It would have taken, like I said, longer than the universe has existed to finish, which is insane. Excuse me. So we better talk about that, right? Why in the world is that not finishing? What is the problem here? So the secret is the fact that there's two recursive calls and that's splitting off and doing a bunch of stuff unnecessarily. All right, so we're actually repeating a bunch of work if you think about it. So let's draw like a diagram for how fib of 5 is going to do its work. Fib of 5, right, we'll go off and call fib of 4 and fib of 3 because it needs to add those two answers together. So fib of 4 gets called first, and then it works on whatever that needs to do. Like it does it all, and then it's going to call fib of 3 right after. Okay. It needs both answers, so we'll call them separately. And then, all right, fib of 4, how does that work? That's again a recursive case call. It's going to call fib of 3 and fib of 2. Get that answer, then it can add them. Okay, and do you see how I've already duplicated a call to fib of 3? That's just going to get worse. Okay, these don't talk to each other. They don't remember their answers. They just get recomputed, and that's the problem here. So fib of 3 is going to go off and call fib of 2 and fib of 1 to add them together. Fib of 2. Fib of 1. Let's see. And then fib of 2 is finally a base case. Fib of 1 is finally a base case, but fib of 2 has got to call fib of 1 and fib of 0. Do you see how a bunch of these are getting called a bunch of times? And then here's fib of 2 again, right here. We'll just have to do it again. That's what's going to happen. It's going to recall everything. Fib of 2 goes off and asks for fib of 1 and fib of 0. Those are your base cases, so we can finally stop there. Do you see the problem? How that's happening? We're repeating a lot of work. It just has to get, all these things get recalled all over again. Then fib of 3, do it again. All right. Fib of 3 is going to go off and call fib of 2 and fib of 1. Disgusting, right? And then fib of 2 goes off and calls fib of 1 and fib of 0. And then finally there's all your base cases. Then it can unwind and do the right thing. So, okay. That is a problem for us, is it not? So let's see, is this big enough? Yeah. Look at fib of 2. Look at all the base cases first. Like fib of 1, bunch of times. Fib of 0, bunch of times. We got to recall all these functions, even though we know the answer the first time we see it. Like fib of 2, it's even worse. You're doing all this work all these times. Fib of 2, there's another call to fib of 2, disgusting. Then fib of 3, even worse, right? There's a fib of 3 call. We're doing all that all over again right here. Disgusting. And then you can imagine that if we were in fib of 6, it would call fib of 5, 6. It would call fib of 5, and then fib of 4 would go all over again right there. So you're doubling the work every time you call a bigger number. Do you see that? That's unfortunate. More or less doubling at least. It's like it's a lean towards this side because that's the bigger number, but more or less you're doubling your work. All right, that's a good approximation. Fib of n plus 1 is double as hard to compute as fib of n. Do you see it? And so that repeated doubling gets very, very bad. This is doable. This take longer than the universe has existed. All right, we'll all be dead, long gone. All the stars anywhere near us will have burned out by the time this is finished. Okay, so that's disgusting. There is a way to fix it and keep it recursive. All right, but sadly, I cannot teach it to you in this class. You'll have to wait until either CSCI 41 or like 45, I would say. That would tell you how to solve this problem. But that's enough for now. You just kind of like save away your answer. If you ever compute fib of 2, like don't come back to it. I know the answer. Just read off the answer. Like you save a little cheat sheet for yourself. That's essentially the answer of solving this and keeping it recursive. But that is as much as I think I want to say about that. So that's why it's bad. There are answers, but you have to wait, all right? So with that, I just have some more examples of recursion. All right, so let's make just to get practice with it and understanding how to break down recursive problems. That's very important. So here's just a more simple example. Let's make a program that prints this time. A program that prints from 1 to some number in order. Like here's what it's going to be called. Print from 1 to, and we give a number here, and the job of it is going to look like this. Like print from 1 to, and then like 5. And its goal then is to print on their screen 1, 2, 3, 4, 5. All right. So this is what it should look like. There's the answer. Do you see the recursive case? Do you see a smaller printing from 1 to something inside of this? You're usually looking for the next smaller one. Do you see it? There's print from 1 to 4 right there. And then the rest are there too. 1 to 3, 1 to 2, 1 to 1. They're all in there. But that's going to be our recursive case. Do you see it? So recursively, in general, you're going to recursively print from 1 to your smaller number if somebody asks you to print up to n. Yeah. And then, after that's done, after your smaller thing's done, you print your n. That's the one bigger thing that you haven't done yet. All right? And you just get to assume that this call works. Assume this works. It will do the right thing as long as you build up the answer correctly. That's the magic of recursion. You have to believe in it. Okay? So yeah, there's that. And then we have to think about the base case. When does it get so small that we're done? So in general, what the recursive case will do is like, all right, to print from 1 to 5, I will first print from 1 to 4, then print the 5. And then to print from 1 to 4, I'll first print from 1 to 3. First print from 1 to 2. First print from 1 to 1. That could be a base case, technically, printing from 1 to 1. But you could go even further than that. Like, let's print from 1 to 0 in order. That would work. And that's an easy base case. If n is 0, and somebody asks you to print from 1 to 0 in ascending order, there are no numbers in ascending order from 1 to 0, so your base case turns into you doing nothing. And it will work. Does that make sense? That's wild. That's really cool. And that's what's going to happen here. That's the easiest way, I would say, to do it. Because then you can just have an empty body, or just like skip over that entire case. That's pretty cool. So let's make that one. Recursive printing. .cpp. Did I spell that right? Recursive printing. All right. So yeah, let's make print from 1 to, like, call it with 5. Might as well copy and paste this. And then, yeah, the job is going to be, like, are we in the base case or are we in the recursive case? If n is 0, we want to print from 1 to 0 in ascending order. Do nothing at all. I'll just have an empty body. That's fine. Otherwise, that's the recursive case. I would like to do the following. I need to print from 1 to the smaller number, 1 to n minus 1, and then it's my number's turn, my original bigger number's turn. So recursively, print from 1 to n minus 1, and then after that, print my n, which is the bigger number. That's the one thing that the recursive job did not complete. That's how I build up my answer. So I need to call myself, right? That my job is to print from 1 to something. I'll just call myself one, the smaller number, and I get to assume that that really will print from 1 to n minus 1. It'll do the right thing as long as I build up the answer correctly using that. So like, all right, this will print from 1 to n minus 1, or 1 to 4 if it's 5. And then my job is to print the last thing, the n, the 5. And that'll just be a cout. Cout n, new line, after that's done though. Okay? So yeah, that's the order of it. That's how it should work, and I'm calling it down there in main. Whee, there we go. 1 through 5, and it will work for any numbers. I hope that makes sense. So yeah, that's how that works. A nice empty base case. That's fun. So technically, you could just like check to see if you're not in the base case. And then you could have just one if body. You don't even need this blank thing. If you did it a little bit fancier, but this is a good example. And yeah, let's just to remember, let's draw the stack diagram. Let's pretend that our printing function is called p. It's like our problem is called p, and we called p of 5. It's easier for me to draw that way. All right. So main was calling for us. We called p of 5. Print from 1 to 5. So 5 was the argument going into the parameter. And all right, here we are, P of 5, 5's not 0, so I'm going to first call this to finish the call to completion, print from 1 to 4, P of 4, and then then it's time to print my n. So this P of 5 is going to go off and call P of 4. It needs to go and do the work first. It cannot finish. It cannot continue until this is done. Right? So P of 5 is waiting on P of 4 on this line. Okay? And then likewise, P of 4 will go off, call P of 3. Because again, 4 is not 0. It needs to call print from 1 to 3 before it can print its 4. So it's going to be stuck and waiting here for P of 3 to complete. Okay? And then print from 1 to 3 first requires you to print from 1 to 2. It's going to be stuck waiting here. So P of 2 happens next. So there's that one. And then it just keeps going, right? Now we're at P of 2. 2 is not 0. So print from 1 to 1 in order. P of 1 gets called. And then finally, we're in P of 1, where, again, we have a different parameter each time. So n is now 1 here. And, all right, 1 is still not 0. So I'm going to recursively print from 1 to 0 before I can print my 1. See that? So, again, it's waiting on this line. It calls P of 0. And that's the base case. So everybody down here, all these guys, they are waiting on the person above them on this line. They cannot complete and print their own number yet. You see it? So, all right, finally, P of 0. 0 is 0. Base case does nothing. It returns having done nothing at all. And like, here's the terminal screen. We've printed nothing. Now we're back in P of 1. It was waiting on P of 0. It's done. Now it can print its n, which is 1, and complete. So we see 1 printed to the screen. Done. Check. Now we're back in P of 2, who is waiting for P of 1. It's done. Now it can print its 2 and be done with its own stuff. Bam. And then it's P of 3's time to shine. All right? P of 3 gets to go, and it's going to go off. And my lights just flickered, by the way. Hopefully this is all still recording. Let's double check. I think it's happy for now. That was wild. So, okay, we're back in P of 3. P of 3 goes, and it was waiting, print P of 2. It just printed from 1 to 2. That's finished. You see it correctly did it, by the way. And then we're here, see out our 3, because that's what n is now. And then we're in P of 4. It was waiting on P of 3. It's completed, correctly printed from 1 to 3. See how you get to assume it works? It really will work if you build it up correctly. Now we're back in P of 4, and it can print its 4. It's happy. Done. And now we're in P of 5, who's waiting on P of 4 to print from 1 to 4. That is completed. Now it can finally print its 5. It was waiting so patiently. And then it can also be done itself. And now we're back in main. The call is completed. All right? So that's why it works. And yeah, I hope that's just ringing bells and it's making sense. Okay? So here, I now have a problem for you. Oh, that bothers me that I didn't get the top of it. Let's try again. And there we go. Here's the code. You can stare at it while you're thinking about it, but I highly encourage you to pause the video and try this out. So here's my question for you. Please, in the similar vein, come up with a recursive solution to a printing from 1 to n in reverse order problem. So not 1 to n, but n down to 1. So like, if you call your print from 1 to n in reverse order on 5, it should print 5, 4, 3, 2, 1. Okay? Oh, sorry. I gave an answer away. Excuse me. My bad. So yeah, think about what P of 5 should look like. Pretend I didn't say anything. And then go and find the smaller recursive call and code it up, please. Do you see it? So yeah, P of 5. If you didn't catch that, of course you did. My bad. I was just too happy to show it to you. That's what it should look like, right? Printing in reverse order. And where's the smaller call now? Like, where's P of 4, if you think about it that way? That's printing from 1 to 4 in reverse order. That is still there. It's just below the 5. Do you see the difference? This one, your 5 is after the recursive call does its work. This one, your 5 is first before the recursive call does its work. Does that make sense to you? So that's going to be the secret. And it's very interesting to talk about because really it's the same answer. It's just you've swapped these two lines. All right. And so if you run into issues with order, like think about what needs to happen before other things. Because like if you swap these two lines accidentally, it will print in reverse order, and I will show that to you now. Okay. So yeah, in general, let's see, how do I want to do this? I guess here, let's steal this. So I need to draw it again. Anyway, we've noticed that there's your P of 5. For example. And what we'd like to do in the recursive case, do you see the order? First you print your n, like P of 5, you got to print the 5 first now. That's the biggest thing. And then you print recursively in reverse order from n minus 1 to 1. See how that's going to work? Because there's your recursive call, there's your P of 4. It's coming after you've printed the 5. The order matters a lot here, okay? And likewise, as you break it down to the smaller and smaller cases, you'll eventually get like print from 1 to 0 in reverse order, which is technically correct now, but you could just do nothing again in the base case. You can steal that. You can keep all that as it was. That'll still be fine. And so legitimately the only difference in the code is the name of the function and the order in which you made that recursive call. Because look here, it's coming after the 5, but here it's coming before the 5. That's going to give you order versus reverse order. All right, that's the only difference. I will prove that to you. There we go. So I'll call this print from, or let's start it, reverse print from 1, 2. Okay, that'll be its name. And so there's that one. Oops. Reverse print from 1, 2. And so the order in the recursive case is that, right? In reverse order. Does that make sense? Do you see the difference? There is no difference, really. It's just these two lines have been swapped because the order mattered. For let's have the new one on the left, and then here's the old one on the right. Compare. For the new one, it's like base case, still do nothing either way. But in the recursive case, the bigger thing comes first. You have to print out your own number n. That's the bigger thing, and then you can recursively print from 1 to n minus 1 in that reverse order. That's a call to yourself. See it? And then yeah, that's just these two lines being swapped. That's the only thing. That's all that's changed, really. So here, let's call it down here in main. And watch it work. So yeah, if you accidentally swap some lines, you mess up the order, you might have reverse order. You get it for free if you do that. Does that make sense? So yeah, that is hopefully why you can see that this is working out. Please yell at me about any of these problems if you have any questions. I'm happy to help. But yeah, I think that's all that I wanted to say. Just like be very careful about the order. But we noticed it was clear to see like, okay, the recursive case, the smaller problem, it comes after versus it came before. Like if you're paying attention, it will work out. Okay, so yeah, I think let's just have some more fun with other types. Now let's do recursive printing of like a string. I think that would be fun. So let's recursively print the characters of a string in order. All right. Though I know you could do this with a loop. This is just practice with recursion. All right, let's say we've got like a string s. And it's like something short to keep it easier on myself. Let's say that it holds blah. And my job that I want to do is I want to print out the characters of the string, blah, B-L-A-H, in that order. Okay. Do you see a smaller string printing problem? Okay. Do you see, how could you break this string down recursively? Can you think of a smaller string printing problem based on this original string printing problem? And there's honestly a few options. Like here's a smaller string, just BLA, and then here's a smaller string, just LAH. Do you see that? Like your recursive case would be like print the first thing and then print the rest, or print the first characters and then print the last character. You could break it down either way. Let's do the top way. Like first print the B and then recursively print the smaller stuff. Do you see that? Like that's a smaller thing. Like here's a smaller string to go off and print. It will work. It's a little weird, but that can be a recursive case. Print the first character, then print the smaller string recursively. And then the base case is also reasonably simple. Just like you think about, when do I have a string that I can immediately print out? Like, when do I have no need to find a smaller string to print? Well, it's when I have the smallest possible string, when I have an empty string. Right? If your string is empty, you can just do nothing at all. You have successfully printed all the characters of that empty string, haven't you? So yeah, just another do nothing case there. And yeah, there's a bunch of different ways to do it. You could have broken it down this way into everything but the last and the last character. That would also work, but the order changes in which you'd make your recursive call, wouldn't it? So yeah, there's that. And then just like to create, like to break it down into this, and like to create the LAH string, it's that subster function. It's like to give a smaller string to your recursive call, it would look like this. If you say subster, it really normally takes two things, like give it the starting index and how many characters to take. But if you just say one thing, there's a default parameter for the second that will just take till the end. So this is your starting index, and that will create the string LAH by itself. Okay, so that's perfect. That's what we want. It will take from index 1 until the end of the string. That's how you can chop off the first character, and that will turn into a nice function for us. I guess I'll make a new file. I want to do string stuff, and then here is here's my string. I would like to say print the characters of S recursively, please. And that'll be a void function again. And it'll take a string, but we can take it by constant reference because we're just looking at it. We're not changing it. And this will be recursive. So we have a base case and a recursive case. We want to print all the characters in order. I know this is a silly problem, but it's a good example still. So if the string is empty, that's your base case. You have nothing to print. And so you'll just do nothing. Otherwise, that's the recursive case. What will you do? You want to, the way that we've chosen to break it down, print the first character, then recursively print the rest, the smaller string. See, that's what's getting smaller, the string itself. There always needs to be something getting smaller, though. Print the first character, and then print recursively. Print the rest of the strings. Print the smaller string. And whenever I say recursively, that means make a call to yourself on a smaller input. You just get to assume that's going to do the right thing. And it really will, as long as you believe in the magic of recursion. It really will work as long as you build up the right answer. Okay? Based on that. So how do you print the first character of any string? Just set S at 0. Then to recursively print the smaller string, well, that's my problem. I'll just call myself on a smaller version. The one smaller version with like the B chopped off. That's this subster call. And that will create a smaller string and not touch the original. It makes a copy, so that's perfect. So there I am, calling it. And what do you know? There it goes. So yeah, that's a nice example of using a different type to do similar things. So there's that one. And you better believe we can do it in reverse, right? So, okay, and it's just going to be us swapping it, won't it? It's really just going to be us swapping things. So here, steal most of this. So here's my string. Let's say that I break it down in the same way again. You could have broken it down in the opposite way, but this will work still. So what changes if I want to print the characters of the string in reverse order? I want to print like halb out. Well, this is the smaller string, it's LAH. Where is it being printed in reverse order? It's right here. Do you see that the recursive call happens first now? Recursively print the smaller string in reverse, backwards, then call yourself. Just like the backwardsness comes from the order in which you make the recursive call. It's like either it's coming after the first character or before the first character. That's the only thing that's different. Isn't that fun? So yeah, very simple to do it in reverse with that in mind. It's like, give it a new name. And be consistent with that name. Oh man. There we go. And it really is that. That's the only difference. Put smaller string in reverse, of course, this time. And that's it. That's what we noticed we needed anyway. Just like, all right, the first thing, print the smaller string in reverse, then my first character. Done. Base case is still the same. To print all the characters of an empty string in reverse order, there's still nothing to do, right? So beautiful. Let's call that and watch it work. And there we go. We get our hulb. Lovely. Okay, I think you can see how very important it is to worry about ordering. But yeah, just get to pretend that the smaller call really will do the right thing. It really will work out as long as you build up the answer correctly. Okay, so for my next question for you, I'd like you to just brainstorm about something. I'd like you to come up with a recursive algorithm to capitalize a string. Do not try to do it in C++ though, because it will not work on the normal string type. Unless you do something very weird. All right, I need to talk about the weird thing. But just like in general, in English, it makes sense to talk about this recursive. Let's say that this is my string, my favorite, and like you can still break it down in the same way, probably. But like the goal is to somehow, by the time your function's done, to have capitalized in a recursive way the entire string. So can you come up with a recursive algorithm? Think about the recursive case. Think about the base case. Like, this is your problem, right? This is your problem P. When I say, like, what's P of S? Okay? That's just what I mean by that. So yeah, what does P of S look like when it's blah? And again, I jumped the gun, I'm sorry. That's what it should look like. That's what should happen. I've given it to you already. But, like, where's the smaller call? What's the order of it all? How would you do it? Okay? Think of it that way. All right. So yeah, let's talk about it. Do you see it? So again, if you break down the string in this way into the first character and the rest of the string, the order doesn't really matter anymore because you just want to achieve an effect. So recursive case. The order doesn't actually matter. You could either like recursively capitalize all these guys and then do the B, the first thing, or you could first capitalize the B and then recursively capitalize everything else. You're just trying to achieve the total effect of the entire string being capitalized. You see that the order in which you capitalize those letters does not matter. So just in some order, you must do the following, right? You want to capitalize the first character, and then you want to capitalize the rest of the string recursively. There's your smaller string, hand it off to your problem. Capitalize the rest of the string recursively. All right? So yeah, in any order, it doesn't matter if this one or that one comes first. As long as the total effect has been achieved, we're good. Okay? I hope that makes sense. Unfortunately, you can't really pass that in any normal way, because like that subster is making a brand new string to work with. You can't like mess with the original string. You could maybe pass along an index that you're currently working on, like that would make it work for normal strings. But honestly, let's talk about this in terms of C strings, because it's honestly simpler. Like you only need one parameter still. So here, let's say that we've got a C string and we want to capitalize that. So what does a C string look like, by the way, if it's holding blah? B, L, A, H, and then \0, right? That null terminator character. So you can still break down the string in this form, like the first character or the rest of the string. That's still fine. Our end goal is the following, right? We want to turn this into the following C string. All caps B, L, A, H. And it's still a C string, so it still has the null terminator. That's never changing. Okay? So, okay. The recursive case, as you can expect, is going to be, in some order, capitalize the first character, and then recursively capitalize the smaller string. So make that call. That's exactly what we discussed, just like the devil is in the details. We'll get to that. And then the base case is going to be a little bit different for C strings. It's like, when do I know I don't have anything to capitalize? It's when I have the empty string, But the empty string is something as a C string. It's just the string with the null terminator. That's still got to be in there. Does that make sense? So you could use like strlen to tell you that. You can use a library function, or you could just go looking at, like, your string is empty if its first character at index 0 is that null terminator. So that's the base case, but the implementation, again, will get a little weird. And so yeah, what a C string kind of looks like, you can represent it as a pointer to its first character, okay? And that's what's going to give us the ability to pass along the smaller string. So this is not correct C++ code, but it's morally correct, so I'm going to use it. Like, here's my char star S2. You can't actually do this in C++. You got to make a char array at the start, but like, you can assign it into this, a char star, eventually. But here's what it looks like in memory, right? Secretly, S2 is a pointer to the C string. It's a pointer to its start. So if it's ABC, it looks like in memory the following: A, B, C, null terminator, and these all have addresses. They're byte addresses. 101, 102, 103. And so S2 holds as a pointer. It holds the starting address of the string, holds 100, and that's what we're calling our capitalize function on. Does that make sense? That's what we're calling our capitalize function on, like the starting address of this place in memory. That's what it looks like. And so that means then, how do I pass along the next smaller string, like from the B onwards? I just need to pass along a pointer to that B, because that's what it means to be a C string. I'm a pointer to the start of it. So you're going to do some pointer arithmetic. S2 plus 1, your original string's address plus 1, gives you this. And that, for all intents and purposes, looks like that smaller string. That's what you'll pass. That is the smaller string. It really is. So that's the reason, because C strings are represented as pointers to the start of them in memory. Like, the smaller string is one after your current first character. Like, just start there instead. That's your smaller string. You see it? That's the secret. So your smaller string in general is S plus 1. That will compute the next address. And that we can code. All right, it's a little weird, but that's what we can do. So here, where do I want to put this? I'll make a new file. So I'm not using strings, but I'm using C strings, and I want to use strlen. I think that will be the easiest. And then CC type for to upper. So here's my string as a C string, and then I can say capitalize on S, and then that should change it if I reprint it out. So it's a void function, capitalize, and it takes a C string. It's a char star. Takes the address of its start. I'll call it stir. All right, so this is being passed. S by itself is the address of the start in memory. That's what a C string is. And then it's either base case or recursive case. It's base case if it's empty, and one way to check for emptiness is like if strlen on that string is 0. Because strlen gives you how many real characters are in it. If it's immediately the null terminator, then it's 0. And that's your base case. Where there's nothing to capitalize, do nothing. But there are other ways to check for this without using the library. You could have said like if stir of 0, like if it's immediately the null terminator, then it's also empty. Like that's a little bit faster because you don't have to do a function call, but this way makes sense, right? Otherwise, recursive case, what do we got to do? We have to, in some order, doesn't matter, capitalize the start of the string. So stir of 0, first character, equals itself, but capitalized to upper. And then recursively capitalize the smaller string, which is a call to ourselves on the smaller string represented in memory as a pointer to its beginning. If the pointer to the beginning of the whole string is stir, then a pointer to the smaller string, the character right after, starting at the character right after me, is stir plus 1. Okay? That's the name of the game there. And that will do it. And it's yelling blah at us now. And it worked. Beautiful. So I hope that makes sense. And that's how you pass along the smaller string. You give addresses. Okay? So I think that is what I wanted to say for this set of slides. Or sorry, for this particular slide. I'm not done with slides yet. The next example we're finally ready for. All right, so you have probably been rolling your eyes at me by now. It's like this is the stupidest way of writing this function. It did not need to be recursive. This is dumb as well. It did not need to be recursive. I could have used a for loop. I don't care. All right. Fibonacci, disgusting anyway. I could have made the for loop and it would have finished by the time, like, in a nanosecond. I don't care about recursion. Here is your reason to care about recursion. Here is a problem you cannot solve without recursion. All right. You're finally ready to understand it. It's going to be a little complicated. All right. Here, the problem is we would like to scramble the characters of a word and give back every possible scrambling. Another word for that is give back all the permutations of the letters in a word. Okay. So I would like to make a function called perms that takes an original string and it gives back a vector of all the different ways you could have jumbled the characters of that string. Okay, do you understand the problem? Like if you called it with this, perms on ABC, its job is to compute the following. A vector containing all the different ways that you could have scrambled these letters. It could have been in the same order, right? Or maybe the last two got flopped, C and B. Or maybe B came first, then it's BAC, BCA. C could have come first, CAB, CBA. And those are the 6 possible ones because it's 3 different characters. 3 factorial is 6. Okay? That's the job of this function. You cannot do this with normal for loops or while loops. You have to use recursion, all right? I promise. This is why we're learning it, when you have problems like this. All right, so I claim, first of all, that this is a recursive problem. So where is the smaller word scrambling problem? One that asks for smaller words to be scrambled, and I use that in the bigger solution. Well, I kind of said it already, actually. It's just like, all right, if you're trying to compute all the different jumblings of ABC, you kind of need to fix one character. Like, pretend that A is coming first, because then, do you see, you could start jumbling the B and the C. Those are the 2 different ways to jumble B and C, just like tack an A at the start. There's your recursive call. Jumble those guys. Same with this, like, all right, fix B at the start, and then go and jumble the A and the C. Here are the 2 ways to do that. Tack a B at the start of that. Those are 2 more options. You see it? And then finally, like, fix C, and then jumble A and B. Attach a C to the start of all of your options. There's your recursive rules, okay? And then the other thing is, like, what's the base case? When is there nothing to scramble? Like, when are you done? You have the answer in front of you. It's when you have the empty string. Okay, so like, if somebody asks you for all the ways to permute the characters of the empty string, all 0 characters of them, there's only one way to do it, right? You give back a vector containing all the different scramblings. There is just the empty string. There's only one way to scramble the empty string. There's nothing. You just give back the same thing, yeah? So that's the base case, okay? I hope you see it. And now the recursive case is hard, all right? It's going to require a for loop, but also recursive calls, okay? So, because we have to loop through every possible character, and they all get a chance at being fixed at the start of our result string. You see it? The A's, the B's, and the C's. And you go and jumble the rest of them, okay? So here's kind of the setup. You're going to fix a starting character, and you're going to try them all. So like, you're going to loop over every character anyway. Like, let's say we're on the first character for now. So like, you choose A. Like, that's coming first right now. You fixed the A. And then you like chop off the A and make the smaller string. Like, all right, everything but the A means I need to scramble. There's my smaller string to scramble. It's BC. Okay, scramble BC. And there's your smaller problem. You go hand that off. You get the recursive answer back. That's going to be, all right, all the ways to scramble BC are BC and CB. So you've got that out. And then you tack an A at the start of all of them. And so you add to your final answer. You're not done yet because you have to try everybody to go first. But like, some of your final answer is now an A at the start of both of these guys. So ABC and ACB. Is that making a little bit of sense? This is a very complicated problem. I would not dream of asking you this on a test. But this is a very, very good example of you need recursion for this. You cannot do it without recursion. Or faking it in some way anyway. It's still recursive. All right, so yeah, that's it. You're going to build up your result vector just like that. All right, you're going to give everybody a chance. Choose A, scramble the rest. Choose B, scramble the rest. Choose C, scramble the rest. Keep on adding what you come up with to your final answer. Then once you've given everybody a chance, you've scrambled everything up, then you return that big vector that you've generated. So here, let's do it together. It's okay if you don't fully understand this, by the way. It's just, this is a great example. I hope you can see. You need recursion. You need to understand it. This is why you need to learn this. All right, so let's see. I need strings and vectors. So here, if I ask for perms of ABC, I'm going to get back a vector of all the different ways to do it. Okay? And then, yeah, that's my goal, is to then like go and print them out for every string reference S in V, print them out. Print out all my jumblings, all my permutations. And so, yeah, here's the setup for the function. And we are ready. So again, I mean, it's still a recursive function. So either we're in the base case or the recursive case. It's just the recursive case is going to be long. So if we're in the base case, S is empty. So if S is empty, I'm in the base case. And the answer is this, a vector containing just the empty string. Okay? So I could just return that on a return line, but I'll just for fun, just to make it look like the recursive case, I'll say vector string result equals that exact vector. Oops. And then I'll return that. Okay, that's the base case. Otherwise, recursive case time. Again, we're still going to have like a result vector that starts out empty, though, that we'll keep on adding to. Oops, that we'll keep on adding to, and we'll do our magic, and then it's ready. It's been filled. We'll return result. Okay, so this is the hard part of the recursive case. So what we need to do is try every character, loop through all the characters in the string I'm trying to permute, and let those be the start, and then go scramble the rest. All right, so try every character and scramble the remaining characters. Okay. So all right, let's loop through this entire string, each character of it. For reasons, I'm going to use a loop on indices, because that will help me delete and like pick out the rest of the characters. Like chop off if I'm choosing B at the start, chop off the B to compute the AC string. Indices will help with that. So I'll say for int I equals 0, I is less than s dot size, I plus plus. All right, and then okay, the character I'm looking at that I'm going to pretend to be at the start now that I'm going to fix is s at I. All right, that's the one I'm going to put at the start. And now, so like I've chosen the B, for example. Now I want to chop off the B and make the string AC, so I can go scramble those guys and tack the B at the start. All right. Or if I've just chosen the A, go and tack off the A, chop off the A, and compute the string BC, and go and scramble that. So how do I compute that string of the rest of the characters? Remaining characters. Well, it starts off as the original string, then I just chop off the thing at index I, because that's the character I'm going to save away for the start right now. So take this and then erase. It's going to be remaining characters dot erase one character at index I. So starting at index I, remove one character. That will remove this character from that remaining character string. All right. So now, like for example, if it was the C that I chose to be at the start, then it just made the string AB. It chopped off the C. Okay. And then, all right, what do we do next? It's going to be, I need to recursively now make a call on the remaining characters. So like, here's my remaining characters. I need to scramble them, because that's going to give me part of my answer. I need to tack the starting character at the start of its scrambling. Okay? So take that remaining characters and call perms on it. That's me. Recursively call on remaining characters, and that's going to give me a vector. That's what my function is promising to do. Give me back a vector of strings of all the jumblings of that smaller string. Smaller string perms, I'll call it. Equals that. And so that is the vector containing like BC and CB, and I'm going to tack my starting character at the start of both of those, and that's part of my answer now. All right? So for every permutation, I'll just loop through it with a range-based for loop. So for every smaller string permutation in smaller string perms, for every permutation in the perms, I want to take this starting character. Like this is now, I'm looking at just the BC, just the CB. I want to take the starting character, put it at the start of that, and add that to my result. My final answer. So add starting char to the front and put it in the result vector. All right, so what I mean by that is result vector, I'm building it up. I want to add a new string to it. Now I have a new string, result.pushback. And right now I'm iterating through all of these smaller string permutations. It's being called smaller string perm. Like maybe it's this one, maybe it's this one. Take your starting character, put it at the start of this, add that to your result vector. That's what I'm doing right now. Pushback, oops, smaller string perm with the starting character at the start of that. Compute that bigger string. So like this is the A, and this is like the BC or the CB. All right, one of those, and then I compute these guys, and those are going into the result vector. That's what's happening right now. Result vector is getting bigger now with a new final answer. This is a new jumbling of my string. Do you see that? And then, once it's done, return result, and that will do it, actually. All right, so I have to zoom out a whole lot to show you the whole thing. There's the function, though. Please yell at me if you have any questions about this. I'm not going to test you on something as hard as this, but this is a very good example of something that you need recursion to do. Like you cannot do it otherwise. So here, let me split screen this way so you can kind of see it. I'll compile and run it. I'll call it scramble. Oops. I'm in the wrong. Oh, I'm in the wrong folder. Silly T-Mux. There we go. Boop. And there it goes. That's working. I hope you can see that. Yeah, sorry, it's a little small. So that's as good as I can do right now. Okay. So there's my jumblings. It's getting all 6 of them. It's trying the A first, the B first, the C first. Isn't that beautiful? It's really working out. It's really doing the right thing, and it will work no matter what. If you have another character at the end there. Oops. Recompile, rerun. Now it's all right. Fix A at the start, and then go jumble BCD. Those are all your options, right? That one, that one, that one, that one. There's 6 options for if you're jumbling 3 characters. So 6 options when A comes first, 6 options when B comes first, and you jumble the rest of them. It's always going to work. Isn't that really cool? I think it's really cool. So let's bring it back to normal. Like it works for any amount. Boop. Just like that. And it's going to do the right thing. Okay? So yeah, that's the code that does it. I hope it makes at least a little bit of sense. But like the magic of recursion is happening right there. When I'm making the recursive call on the smaller string, it is magically jumbling the rest of them. It's making it happen. I don't have to expend any thought thinking about how it does it. I just get to assume, right? Due to the magic of recursion, this is a smaller string. I get to assume it's going to do the right thing, as long as I use that smaller answer to build up the final bigger answer. And it did. It's hard to even explain what it's doing, right? But it's going to do the right thing. I get to assume it works, and it really did. Okay, so that's magical. That's really cool. I hope you enjoyed it as much as I did. That's a good example. And then there's also this example. It's called the Tower of Hanoi. It's a game. Maybe you've heard of it before. It's a game where you've got a bunch of little, you got 3 pegs, and you got a bunch of discs that you start stacked on one peg. And the rules of the game of Tower of Hanoi, by the way, I'm not going to test you on this one. This is just a standard example. You can find a bunch of cool animations on the internet, and I'm sure your book will talk about it. It is just a classic example of recursion. This is another example of a recursive problem that you cannot solve without recursion. Okay, so that's just another good example. So yeah, I just want you to hear about it. I'm not going to test you on it. But the name of the game, Tower of Hanoi problem, is like you're going to write a function to tell you how to properly play this game. Here's the rules of the game if you haven't heard of it before. You got all these things, all these disks stacked on one peg, and the rule is that you want to move this entire stack over to here while playing by the rules. So here's like, the rule is you can put a disk on an empty peg for sure. That's fine. Now this one's gone. But you cannot put a bigger disk. You cannot move that one onto here. You cannot put a bigger disk on top of a smaller disk. Like that second one would have had to go over here, and then you could put the smaller disk on top of it. Those are your rules. Okay, you can move one at a time, and you can only put smaller disks on top of bigger disks. And so, yeah, that's your goal. And you get a middle peg to do some intermediate scratch work on. But your goal is to move all this guy over to here. Okay? And this is a recursive problem. You can write a program that will tell you exactly what moves to make to solve this, to move this entire stack over to here. All right? And you could not do this with a normal loop. You have to use recursion. And so here, here's kind of the setup. You've got like a source peg, a destination peg where you want everything, and then here's like an intermediate peg where you can do some scratch work. All right. So the base case is whenever you're trying to move the smallest peg. You can move this guy anywhere. Either it's empty or like you've got bigger things underneath it. You're good. So that's the base case for the smallest peg. And then here's the recursive case. I hope you can kind of see me break it down. It's like recursively, you see how you could break down this entire stack like we've been doing with strings. You can break it down into everybody but the last biggest disk and the biggest disk. So here's the setup. Here's your recursive answer now. It's like, all right, move this one smaller stack, all that guy, onto the intermediate peg. Just like let the magic of recursion put it there. Now it's there, okay? Take all that, move it to there. Does that make sense? So you can make a recursive call to do that, and it will just like make it happen, using destination as your intermediate peg for that call. And then now you've freed up this biggest disk, which you can then place over here. Beautiful. And then, yeah, so now here's your setup. You've got, this is all empty now. Like this is blank. You move the biggest disk here, the smaller disk there, and now you just make one more recursive call. You move this stack, this entire stack, over onto this. It's fine now because the biggest disk doesn't pose a problem. Using this one as the intermediate peg because now it's empty. Does that make a little bit of sense? That's the secret. So again, you can use recursion. It's going to be a lot of moves. It takes a lot of moves to play this game, but it will tell you exactly what moves to make. Like move the thing at the top of this peg to this peg now, and that's it. All right. So I encourage you to read about it in some form. It's a very standard classic example. You'll find some very fun animations and some very insightful videos about this particular problem on the internet, and it can only help you. All right, if you go and look it up. So I think that's where I want to leave us for now. I've shown you a couple cool problems that you cannot solve without recursion, and that is a reason to learn it. You're going to need it in future classes, I promise. You cannot do some things without recursion. Even though a lot of these examples you could have used just a loop for. All right, it's very worth learning. I can guarantee it. And yeah, with that, that's as much as I can try to persuade you. And I think that's all that I have to say. So I'll see you in the next one.